Ever pondered why a day lasts 24 hours? A seemingly simple question, yet the answer takes us on a cosmic journey, one that begins with our closest celestial neighbor, the moon. Our moon, in its silent ballet around the Earth, exerts a profound influence on our planet's rotation. This is all down to a cosmic tug of war, a gravitational dance between the Earth and the moon. You see, when the moon formed about 4.5 billion years ago, it set the Earth spinning at quite a lick. Back then, a new day dawned in less than 10 hours. But the moon's influence didn't end there. Over time, the moon's gravitational pull on Earth's oceans gave rise to what we call tidal bulges. Imagine two mounds of water, one facing the moon and one directly opposite. These bulges, in constant motion as the Earth spins, create a friction between the water and the ocean floor. This friction acts like a cosmic brake, gradually slowing down Earth's rotation. Now, this braking effect is not dramatic. We're talking about a slowdown of roughly 1.7 milliseconds per century. That's less time than it takes a hummingbird to flap its wings once. But multiply that by billions of years and you start to see a significant effect. And this is where we find ourselves today, with the moon's relentless tug adding ever so slightly to the length of our day, year after year, century after century. If left unchecked, this lunar braking effect would eventually stretch our day to more than 60 hours. So if the moon's pull is continuously slowing Earth's rotation, why isn't our day getting noticeably longer? Let's dig a little deeper. This is where our story takes an unexpected turn, as we look not to the moon, but to the sun, and the power of atmospheric tides. But that's a tale for the next scene. The sun, it turns out, has a significant role in this cosmic dance. When we think of tides, we often picture the ebb and flow of ocean waters, largely influenced by the moon. But there's a lesser-known player in this symphony of celestial forces, the sun. Solar tides, while generally overshadowed by their lunar counterparts, have a profound impact on our planet's rotation. You see, just as the moon's gravitational pull causes the Earth's oceans to bulge, creating what we know as tides, the sun does the same. However, the sun's tidal effect is less than half as strong as the moon's due to its greater distance from the Earth. So while the sun does contribute to the tides, its influence is often overlooked. But let's turn our attention to a less discussed, yet incredibly important aspect: atmospheric tides. These are bulges in the Earth's atmosphere caused by the heating effect of the sun. Just as water tides are created by the gravitational pull of the moon and sun, atmospheric tides are created by changes in air pressure and temperature. Now here's the kicker. These atmospheric tides can influence the speed at which the Earth rotates. When the moon formed about 4.5 billion years ago, a day on Earth was less than 10 hours. But as the moon's gravitational influence attracted the Earth's oceans, creating tidal bulges and friction with the ocean floor, it acted like a brake, slowing down our planet's rotation. For most of Earth's geological history, lunar tides were dominant, outperforming solar tides by about 10 times. But atmospheric tides, bolstered by the sun, have been silently impacting our planet's rotation speed, resisting the moon's efforts to slow it down. However, something changed about 2 billion years ago that altered this dynamic. 2 billion years ago, our day was only 19.5 hours long. So what happened? The plot thickens when we add the atmospheric temperature into the mix. It appears that the temperature of the Earth's atmosphere had a random but extremely crucial link to the speed of our planet's rotation. This connection played a significant role in determining the length of our day. As the Earth's atmosphere warmed, it began to resonate with the planet's rotation. Now, resonance is essentially the frequency at which waves, such as atmospheric waves, pass through a medium. In this case, the medium was our atmosphere. This resonance corresponded to the length of a day, which was around 10 hours at the time. This warmer atmosphere and its resonance with the Earth's rotation speed resulted in larger atmospheric bulges. Picture these bulges like humps on a camel, but in the atmosphere, created by the gravitational pull of the sun. These bulges increased the sun's tidal attraction, the force it exerts on the Earth due to gravity. You see, the sun, like the moon, also has a tidal influence on Earth, although it's less potent due to the greater distance. These solar tides are relatively small today because the resonance of our atmosphere and the Earth's rotation period of 24 hours are out of sync. But 2 billion years ago, when the day was around 20 hours long, the story was different. The atmospheric tide had grown due to the warmer atmosphere and its resonance with the Earth's rotation. The atmospheric bulges became larger, and the tidal pull of the sun grew strong enough to counteract the moon's influence. This shift in power resulted in a tug-of-war between the sun and the moon. This celestial arm-wrestling match between our closest star and our only natural satellite has shaped the length of our day, from a quick 19.5 hours to the familiar 24 we know today. The sun and the moon, locked in a cosmic struggle, have been shaping our days. Two forces seemingly at odds have created a delicate equilibrium that defines our concept of time. But how did this balance of forces come to be? Let's go back 1 billion years ago. The sun's tidal attraction grew in strength, countering the moon's influence on Earth. This was due to the increased size of atmospheric tides, which were larger because the atmosphere was warmer. The frequency at which waves passed through the atmosphere, its natural resonance, corresponded to the length of the day, which was about 19.5 hours. Now imagine for a moment a seesaw, perfectly balanced in the middle. On one end you have the moon, pulling Earth's oceans, slowing down our planet's rotation and stretching out the day. On the other end you have the sun, its tidal attraction amplified by the warmer atmosphere and its resonance with the day's length. This cosmic seesaw remained in a state of equilibrium for about 1 billion years, with neither the moon nor the sun gaining the upper hand. The result? Our day remained constant at about 19.5 hours. But what would have happened if this balance had not been maintained? Well, without the sun's increased tidal attraction to counter the moon's influence, our day could have stretched to over 60 hours. Imagine that, a single day lasting almost 3 of our current days. However, the delicate balance of forces between the sun and the moon prevented this from happening. The sun's tidal attraction, amplified by the warmer atmosphere and its resonance with the day's length, counterbalanced the moon's slowing influence. This cosmic tug-of-war kept our day at a steady 19.5 hours for 1 billion years. So, the next time you check the time, remember the complex cosmic dance that keeps our days at a comfortable 24 hours? But the dance isn't over yet. You see, the moon is still tugging at our oceans, creating tidal bulges that act like a brake on our spinning planet. This celestial pas de deux is gradually slowing Earth's rotation. The day continues to lengthen, but not at a pace we humans would notice. It's a slow dance, with each day stretching by about 1.7 milliseconds every century. That's about 1 minute every 40,000 years, so no need to adjust your watches just yet. This ongoing evolution is a testament to the dynamic nature of our universe. The forces that shape our days are not static, but constantly in flux, influenced by the intricate ballet of celestial bodies. As we look to the future, remember that our days, like our universe, are in constant motion and evolution.